How do you size the height of a flaw with tip diffraction? Let's take a look. When we think of UT testing in first principles, we're really thinking of reflection. The thing that we're trying to see has to be facing towards us in some manner so that we can bounce sound off of it and receive it. But tip diffracted echoes don't really work that way. Tip diffraction echoes work on something called Huygens principle. Now, I'm not going to explain that in detail, nor will I probably pronounce it correctly. But what's happening is that some of the sound bounces in pure reflection off of the flaw, and some sound at the very end of the flaw misses, but the sound at the very tip will diffract around the end, and actually it acts like a point source, a very faint point source, so you get almost like a satellite or spherical wave of sound coming back. Now there's two things to remember about tip diffraction echoes. Number one, they're very faint. You have to turn your gain way up to see them. Number two is that it's the same wave mode that you used to get there. So if you're testing with angle beam, say for welds, with shear waves, then your tip diffraction echo will be shear waves coming back. It's very difficult, if not impossible, to tell the difference between a reflected and a diffracted echo, but we can use the amplitude as a hint. I'm going to use my Sonotest Veo 3, and I've got 2 transducers and 3 groups set up. The first 2 groups are this probe. This is 5 megahertz, 32 elements with a 0.6 millimeter pitch. And then I've got this probe, which is a 10 megahertz, 32 elements with a 0.3 millimeter pitch. And on the Veo, I've set up the first 2 groups on this probe using 16 elements and then the full 32. And the third group is all 32 of this 10 meg probe. I've got a Flawtech plate here that's 5/8 of an inch thick, 15.9 millimeters. It has a root crack in it. We'll use the same 3 groups, and I'll use the 16 element aperture to start. I'm just going to move it back and forth. And the idea here is it's fairly easy to identify this as a crack. To size the height, what you want to do is find the reflected or tip diffracted signal, which is the furthest distance from the back wall line. So you have to look above the back wall line and below. So as we move the probe back and forth, we can see that we have a large reflector down here. Now that's amplitude is so high, it's probably a reflected signal. Now that's in the second leg, so what's happening is the sound is going down like this, back and up again. That probably indicates the crack has a little bit of a hook on the top. And if we look on the first leg signal, I don't see a whole lot up there. Maybe this one. And we have to sort of gauge which one of these is furthest from the back wall. Now I'm going to go, just because we're talking about tip diffracted echoes, I'm going to go with this one up here. It's very faint, and I'll zoom into the A scan. And you can see there it is right there. And let's see, we'll move our cursor over here. Gate 1 says 12.2 millimeters, 15.9 minus 12.2 is 3.7, so we'll call that a 4 millimeter height. Now let's switch to the 5 megahertz 32 element aperture. The first thing that you notice is that the entire signature for the crack is pushed over further on the S-scan. And this is the downside of using larger probes with big apertures. The center of the beam comes out from the center of the aperture. We're using all 32 elements, so compared to the 16 element aperture, which I did put more towards the top of the probe, this one comes out more towards the backside, which means that I just don't have the approach distance that I want. You will get better height sizing, like we mentioned before. The closer you get and the steeper the angle you get. In this case, I can't really do that, so we get what we get. So if we move the probe back and forth, you can see that as far as tip diffracted echoes go, there is some really faint ones right here at the top, right about there. I'm going to flip over to the A scan. Here it is there. It's coming in, that's gate 3 at 11.4 millimeters. So that's about 4.5 millimeter height. Compared to 4 millimeter height with the 16 element aperture, we're still pretty good. Now we switch to the 10 megahertz probe. This is where the action is because we've got a really nice probe with a very small wedge. I got great approach distance. I can see this crack with all of my angle range, all the way up to some really low angles, say down here to around 49 or 50 degrees. And we've got lots of opportunity to play with all the tip diffracted echoes all along the crack. And in this case, we're gonna go way up here and let's see if I can't see anything further up than that. No, I think that right there is the top of the crack, which are these little faint echoes right in here, we'll switch over and we will peak that right about here, and that's gate 5, and we're looking at about 11.55. We're going to call that 4.4 millimeter crack height. I like it. So that is how you do sizing using tip diffracted echoes. There's also many other things we could get into, like sizing lack of fusion, where you maybe don't have a corner trap signal. We'll get into that in another video. If you enjoyed the video, please hit the like and subscribe buttons, and thanks for watching.